Today, we're tracing this incredible scientific journey of cold and how the search for it, the pursuit of lower and lower temperatures, actually changed everything.
It really did. And this deep dive is a custom exploration of that history. And you're right, it's so much more than just a lot of inventions.
Right.
Our sources detail this just relentless intellectual and experimental quest. And it's what transformed coal from just a feeling into something you can measure, you can control, a scientific cornerstone.
And this quest led to some pretty huge breakthroughs, didn't it?
Oh, absolutely. Things like liquefying gases, which sounds kind of abstract, but it also let us explore these ultra cold regimes where all the, thermal noise just vanishes.
Yeah.
And that's where quantum mechanics really lives.
Okay, so let's unpack this. Our mission today is to chart that shift from ancient ideas all the way to standardized measurement. Then we'll dig into the huge theoretical leaps like thermodynamics and absolute zero.
And finish with that thrilling experimental race to liquefy, well, everything.
I love that frame. So let's start at the beginning. Before we had instruments, how did people even categorize something like cold?
Well, you have to go back to thinkers like Aristotle. For them, cold wasn't just the absence of heat.
It was its own thing.
Exactly. It was an active quality, a fundamental principle. It was intrinsic to elements like water and earth, just like wetness or dryness. It was woven into, everything from natural philosophy to early medicine.
And that view, I imagine, really limits what you can do. You can't really master something if you think of it that way.
You can't. And the shift, the real start of thermal science, came with the invention of the thermometer. Or the thermoscope, right?
Right, from Galileo, around 1592.
Yeah, and those early ones, they could show you that something was getting hotter or colder, but they didn't have standardized scales. So if you and I measured the same thing, we'd get totally different, incomparable readings. Scientifically, it was kind of useless.
So the key wasn't just the device, it was making it consistent.
It was all about consistency. And Daniel Gabriel Fahrenheit in the early 18th century, he's the one who really cracked this reproducibility problem.
So how did he do it? I mean, how do you make a scale that works the same in London as it does in Rome?
He used fixed, stable reference points. 0 degrees on his scale wasn't just some random number. It was the coldest, most stable state he could reliably create in his lab.
Which was?
A mix of ice, water, and ammonium chloride, a freezing salt mixture. Then he set the freezing point of pure water at 32 degrees and body temperature at around 96. By grounding his scale in these physical phenomena that anyone could reproduce.
He created a universal language?
He invented scientific reproducibility for temperature.
Yeah.
A global shared language.
That's a huge deal. And then after Fahrenheit, we get under Celsius. But I heard his original scale was backwards.
It was, yeah. In 1742, he said 0 degrees is the boiling point of water and 100 is freezing.
That feels so wrong.
It does now, yeah. It was actually Carl Linnaeus who flipped it around to the one we all know today. 0 for freezing, 100 for boiling. A really practical, universal bedrock for science.
Okay, so we've got the instrument, but now the intellectual battle starts over what heat and cold actually are. And for a long time, the caloric theory was the big one, right?
It was dominant. The idea that heat was this invisible, self-repellent fluid called caloric. And, it explained a lot of things really well.
Like why a hot cup of coffee warms up your cold hands.
Exactly. The fluid flows from hot to cold. Very tidy theory. But it had one massive problem it just could not explain.
It was friction.
Friction. Benjamin Thompson, or Count Rumford, he noticed this while he was overseeing the boring of cannon barrels. He saw that you could generate a seemingly infinite amount of heat just by drilling metal.
Wait, hold on. Why was that the killer blow? If the theory was so good, why was just drilling a cannon so contradictory?
Because the theory said caloric was a finite fluid. You couldn't create or destroy it. If you can generate endless heat just by doing mechanical work, well, you're creating this fluid out of thin air.
Which violates the rules.
Violates the rules. So Rumford's work really paved the way for the kinetic theory. This revolutionary idea that heat is just the motion, the kinetic energy of the particles inside a substance.
And James Joule is the one who puts the final nail in the coffin for caloric theory.
He does, with his famous paddle wheel experiment. He showed the mechanical equivalent of heat. He quantified very precisely how much mechanical work, literally a weight dropping, it took to raise the temperature of water by 1 degree.
So heat is officially a form of energy.
Exactly, which leads right to the first law of thermodynamics. Energy is conserved. It just transforms from one form to another. Heat was no longer a mysterious fluid, it was just energy.
And once you can quantify it like that, you can create a truly absolute scale.
Right. And that's where William Thomson who we know as Lord Kelvin, comes in. He uses the work of Sadie Carnot on heat engines to define this new standard.
What was so important about Carnot's work on engines for this?
Well, Carnot showed that the maximum efficiency of an engine depends only on the temperature difference between its hot and cold parts. It doesn't matter what substance you're using, water, alcohol, mercury.
So it's independent of the material.
It's independent of the material. So Kelvin realized he could use this principle to define a temperature scale that was based on the laws of physics themselves, not on, how much mercury expands.
And that scale naturally points to an ultimate endpoint, a lowest possible temperature.
It does, absolute zero, roughly minus 273.15 Celsius, the theoretical finish line, the state of minimum energy where all classical motion just stops.
So the map was drawn, and the great experimental race began.
The race to the bottom.
The early groundwork for this was actually laid way back in the 17th century by Robert Boyle, right?
Right.
With his work on gas pressure and volume.
That's right. Boyle's law gave people the first tools for manipulating gases mechanically. But the first real breakthroughs in liquefaction came from Michael Faraday in the 1820s.
He managed to liquefy gases like chlorine,
Sulfur dioxide, a few others. He used a combination of high pressure and cooling. And this was a huge step because it shattered the idea of so-called permanent gases, substances people thought could never be turned into a liquid.
Faraday proved them all wrong.
He proved that, in principle, anything could be liquefied if you could just get it cold enough under the right pressure.
And that just kicked off this insane race for the really tough ones. Oxygen was next.
Right, and in 1877, you had Louis Paul Quétet and Raoul Pictet independently liquefy oxygen, just in these little flashes. But it was proof it could be done.
And then hydrogen.
Hydrogen was James Dewar in 1898, a huge challenge. He had to invent a whole cascading refrigeration system using liquid air as a coolant just to get the hydrogen cold enough to start the final liquefaction process.
But the final boss, the ultimate challenge, was helium.
Helium, yeah. Conquered by Heike-Kamerlingh-Onnes in Leiden in 1908.
And that achievement, getting down to just a few Kelvin, was truly monumental. But it wasn't just about technique. You needed new technology, right? You can't just put liquid hydrogen in a teacup.
Not for long, no.
Yeah.
And this is where necessity really drove invention. The Dewar flask, what we all call a thermos, was invented by James Dewar in 1892.
No way. The thermos bottle is actually a Dewar flask.
It is. That double-wall vacuum design was made specifically to store these ultra-cold liquids by stopping heat transfer. And ironically, he was so bad at patenting his own work that someone else commercialized it, and we ended up calling it a thermos.
That's incredible. So these lab achievements, they don't stay in the lab. They launch actual revolutions that affect every single one of us listening.
I mean, we live in a world that is completely built on the mastery of cold. Think about artificial refrigeration. It comes directly out of this science in the late 19th century.
And that changes everything.
It changes everything. Global food supplies, public health, the growth of cities, it's all tied to being able to preserve food long term.
And if we fast forward to today, cryogenics is central to so much of modern life.
Absolutely. The liquid helium that Onbones first created. Every single MRI machine in every hospital uses it to cool superconducting magnets. It's indispensable for modern medicine.
And liquid nitrogen, too.
Liquid nitrogen is used for everything from cryopreservation of biological samples, blood, stem cells, to cooling high-end electronics.
And on the theory side, understanding that heat was energy gave physics and chemistry this universal currency.
It did. Ideas in chemistry like Hess's law, the fact that the energy cost of a chemical reaction is the same no matter how you get there, that's a direct consequence of the energy conservation rules we figured out by chasing down cold.
And maybe most profoundly, low temperature physics was a direct catalyst for quantum mechanics.
It really was. When you get matter incredibly cold, you silence all that thermal noise, that jiggling. You strip away the classical world. And what's left behind are the pure, weird quantum effects.
Like Bose-Einstein condensates.
Exactly. Where thousands of atoms start acting like one single giant wave. You can only see that at nanokelvin temperatures.
So we've gone all the way from Aristotle's elemental cold, something you feel, to the liquefaction of helium, something you can control down to a fraction of a degree. It's really a triumph of quantitative science over just qualitative feeling.
It is. But, it raises an important question. Even though we have mastered cold down to millikelvin temperatures, the field is still expanding. The chase for even lower temperatures is vital for things like quantum computing, for finding new superconductors.
For exploring totally new states of matter.
Right. So it makes you wonder, What fundamental secrets of the universe are still out there hiding, only revealed when you get things cold enough to make all the thermal energy just go silent?